Right now, as you watch this video, your device is performing a small miracle. It's receiving thousands of tiny fragments of data, each one taking a completely different route through a global maze of cables and routers, arriving out of order, and somehow reassembling them into the smooth video you're watching right now. This is packet switching, and it's the invisible infrastructure that makes the entire internet possible. Without it, there would be no streaming, no social media, no online gaming, basically no modern digital life. They say necessity is the mother of invention. Well, in this case, it was more like paranoia. Hi, my name is Bill, and I'll tell you all about it in this episode of Tone and Light. It all started in the early 1960s, at the height of the Cold War. The RAND Corporation, a think tank that specialized in cheery topics like nuclear warfare, gave a researcher named Paul Barron the assignment to design a communications network that could survive a nuclear first strike. Traditional telephone networks relied on centralized switching stations. The problem was, you destroy a few key hubs and the entire network collapses. It's like a tree. Chop down the trunk and every branch falls with it. Barron had a radical idea. What if there was no center? What if messages could be broken into small chunks and each chunk could find its own way through the network, like water flowing around obstacles? He called it distributed adaptive message block switching. Meanwhile, across the Atlantic, a British researcher named Donald Davies was having the exact same idea, completely independently. In 1965, Davies worked out the practical details and gave it a name that could actually stick: packet switching. And there was a third person working on the same problem simultaneously, Leonard Kleinrock at MIT, who was developing the mathematical foundations for how network traffic actually behaves. 3 researchers, 2 continents, no coordination, and they had the same idea. Kleinrock moved to UCLA, and his team, as we shall see, will be the ones to actually throw the switch. Here's how packet switching actually works. Let's say you're streaming this video. Your device doesn't send that data as one continuous stream. Instead, it breaks it into tiny chunks called packets, usually between 1,000 and 1,500 bytes each. It's like tearing the pages out of a book, putting each page in its own envelope, and mailing the envelopes separately. The envelopes represent the packets. Each packet gets a header, like an address label, that contains 3 critical pieces of information: where it's going, the destination address; where it came from, the source address; and what order it belongs in, the sequence number. Now, here's where it gets interesting. Unlike a traditional phone call, these packets don't follow a predetermined path. Each router along the way looks at the packet and makes a decision. Which way should I send this? It's choosing the best available route at that exact moment based on traffic congestion, broken links, or delays. This is why the internet is so resilient. If part of the network goes down, packets just go around it. They're like water finding the path of least resistance. But this flexibility comes with a trade-off called latency, which is the delay between sending data and receiving it. Because packets can take different routes, they don't all arrive at the same time. Some might take the scenic route through 3 extra routers. Others might hit traffic jams at a congested node. When they arrive at the destination, they're often out of order. Packet 5 might show up before packet 2. So your device has to wait, check these sequence numbers, and reassemble everything in the correct order. A particular packet might not show up at all. In that case, your device has to ask the source to send it again. For most internet activities, a few milliseconds of latency is no big deal. But for real-time applications like video calls or online gaming, latency is a problem. That's why your Zoom call sometimes freezes, or why you blame lag when you lose at Fortnite. This is where packet prioritization comes in. Modern networks don't treat all packets equally. They use something called quality of service, or QoS, to give priority to time-sensitive traffic. Think of it like boarding an airplane. Business class boards first. Video call packets and gaming packets get priority treatment. They jump to the front of the queue at routers. Meanwhile, something like the download for your software update can take a while. It's like flying economy. Your router is constantly making these decisions thousands of times per second, ensuring that your video call stays smooth even while someone else in your house is downloading a massive file. To understand why packet switching was so revolutionary, we need to talk about what it replaced: circuit switching, the technology behind old-school telephone networks. When you made a phone call in the 20th century, the network established a dedicated circuit, a continuous physical connection that stayed reserved for your entire conversation, even when you were silent, even when you were on hold listening to elevator music. This guaranteed quality, but it was incredibly wasteful. It's like reserving an entire highway lane just for your car, even when you're not driving. Instead of reserving bandwidth, packet switching uses statistical multiplexing, where everyone shares the network dynamically. When you're not sending data, the bandwidth is available for everyone else. This efficiency is what makes the modern internet economically viable. Billions of users sharing the same infrastructure, only using bandwidth when they actually need it. In a spectacular failure of imagination, AT&T, the company that controlled American telecommunications at the time, evaluated packet switching, concluded it wouldn't work at scale, and passed on the technology. Talk about being blind to the future. On October 29, 1969, a UCLA graduate student named Charlie Klein, who was part of Leonard Kleinrock's team, sat down at a computer terminal to make history. He was about to send the first message over a network connecting UCLA to Stanford Research Institute about 350 miles away. They called the network ARPANET. The plan was to type login. He typed L, it went through. He typed O, it went through. And then the system crashed. The literal first message ever sent over what would become the internet was lo, as in lo and behold, an accidental and truly poetic beginning to the digital age. They got it working about an hour later, and within a month, 4 computers were connected. Within a few years, ARPANET spanned the country. In 1973, they made the first transatlantic connection linking University College London to California. Here's something that should tell you everything about how completely packet switching won. Right now, as we film this, telephone companies around the world are in the process of shutting down the last circuit switch networks on Earth. The old PSTN, the public switch telephone network made of copper wire with a circuit switched backbone that Bell and its successors spent a century building, is being decommissioned. In the UK, British Telecom is pulling the plug in 2027. In the US, the FCC has been approving shutdowns since 2019. The telephone network is becoming a packet switch network. Barron and Davies didn't just build the internet, they eventually swallowed the phone system too. Winning the packet wars, however, doesn't mean the work is done. In fact, the demands on packet switching are getting harder, not easier. Think about remote surgery. A surgeon in one city operating a robotic scalpel in another, or a fully autonomous vehicle processing sensor data at highway speeds. In those applications, you need the network to guarantee delivery within a specific time window. Not just probably fast, but deterministically and measurably fast. Standard packet switching by design can't do that. It's statistically good, but it's not guaranteed. So engineers are retrofitting the rules. They've created standards like time-sensitive networking, or TSN, which use precise clock synchronization and guaranteed delivery windows. 5G networks are introducing something called network slicing, the ability to carve the physical infrastructure into virtual lanes with different performance guarantees. One slice for your smartphone download, another slice with sub-millisecond latency reserved for the autonomous vehicle beside you on the highway. And even the underlying plumbing is being modified. TCP, the protocol that's been reassembling your packets in the right order since the 1970s, is being enhanced by a newer protocol called QIC, or QUIC. Developed by Google and now standardized as the backbone of the World Wide Web, QUIC fixes TCP's biggest flaw. When one packet in a stream gets lost, TCP stalls everything while it waits for it to be resent. QUIC lets other data streams keep moving. Google, YouTube, Facebook, they're all running on it. You've been using it for years without even knowing. So here's where we are. Packet switching is 60 years old. It runs virtually every network on Earth, and it's still being actively redesigned to handle things its inventors never imagined. Paul Barron wanted to survive a nuclear war. What the engineers working on TSN and QUIC and 5G network slicing are trying to survive is a world where the network has to be fast enough for a robot to perform surgery and reliable enough for a car to make a split-second decision, all on the same infrastructure simultaneously. That's not a network that's finished. That's a network that's still evolving. And that's exactly the kind of story we're here to tell. The hidden systems still being built underneath modern life. Thank you for watching. If you enjoyed this video, please like, subscribe, ring the bell, and share. We've got more stories about the hidden systems that make modern life possible. Stay curious, and I'll join you in the next episode of Tone and Light.